yeah, I don't know if you could hear me. I said, yeah.
Okay. Yeah, I can hear you. Perfect. Okay. So hello, good morning, everybody. I hope you guys are doing well. So we'll get started with just a couple quick announcements and then we'll get rolling. So first, I want to remind you that your Chapter 4 quiz is on Monday. So it's the same as the others where it'll open at midnight and sort of Sunday night, midnight, 12:01, and be open till 11:59 p.m. So you'll have to find a 1-hour block to take that quiz. And then also, William will be conducting the Chapter 4 review tonight. The link is in Moodle. And so that review is posted in Moodle if you want to try it beforehand. So you can check that out tonight at 5. Go to his review. And if you can't make it, I will post the recording of the review probably at some point tomorrow. So that is coming up. Today we are going to be starting Chapter 5, which is obviously not on your Chapter 4 quiz. So the stuff that we do today will be on the mini quiz for Sunday, but not on Monday's chapter quiz. So I want to just give you sort of an overview of what Chapter 5 is going to do for us, what it's going to tell us. So Chapter 5 is going to take the approach of, now that we know how to find all these derivatives, right? We've spent all this time computing them and looking for them. We want to ask the question, what if we start with the derivative? What if we have information about the derivative? What will that tell us about the original function? And we've done this a little bit through our graphing. We know that if the first derivative is positive, that the original function is increasing. We know if the first derivative is negative, that the original function is decreasing. But we want to see if we can get some more solid information about the original function if we have information about the derivative. So that's the sort of take of Chapter 5. So we're going to be starting with derivatives and sort of thinking about what that will tell us conceptually about the original function. So I'm going to go ahead and switch over to my DocCam. I'm going to turn off my own video just for bandwidth. So this particular section is called Distance and Accumulated Change. So distance is sort of the fundamental premise that we use to conceptualize what is happening. And to start thinking about this, we consider the fact from physics that distance equals velocity times time. So if you're walking 5 miles an hour and you walk for 3 hours, you've gone 15 miles, right? So your velocity is how quickly your position is changing, and you multiply that by the amount of time that you are going that distance, and that gives you your total distance traveled. So if you know your speed and you know how long you're at that speed, you are taking information about the derivative, your velocity, and you are getting information about the original function, your position. So when we talk about how much your distance changed, we are talking about how much the position changed. Okay, so we're going to do a couple of examples that use this idea of distance equals velocity times time, and then we'll expand it to show that if you have any rate times time, that we can then use that to talk about the original function. So we start with this idea that if you were going to travel 40 miles per hour for 3 hours, how far did you travel, right? So you would take your rate, so we have 40 miles per hour, times your time, you did that for 3 hours. Now, if we were to multiply these together, we can see that the hours units will cancel, and we get 120 miles, right? M was for miles. So you traveled 120 miles during this 3-hour period. So this 40 miles per hour was your velocity, and 120 miles, which is how far you went, talks about your position, your change in position, okay? So by taking information about our derivative, velocity, we're able to tell something about the original function, which is position. And what we're able to tell is how much that original function changes, okay? How do we represent this graphically? So we're introducing a new way to think about this through graphing, okay? So when we have this type of problem, we want to graph our rate or our derivative versus time. Okay, so for this particular problem, our rate was 40 miles per hour. Well, 40 is a constant, right? We want this constant rate. And when you draw a constant, that's just a horizontal line. And so our time, we have 1, 2. So from time equals 0 to time equals 3, that's 3 hours. So we have this constant rate for 3 hours, okay? When we graph the rate versus the time, it turns out that if we were to find what's called the area under the function, we can do that geometrically because we have a rectangle. So if we do 40 times 3, we get 120, which is the same as what we got up here by multiplying our rate times our time. It turns out that if we were to look at what's called the area under the curve, which is a rectangle here, that area under the derivative function will tell us how much the original function has changed. Okay, it's a really interesting concept here. So we're going to try this out with the next example where we're going to do something very similar, but now we're going to have 2 legs on our trip. So suppose you want to travel 20 miles per hour for 3 hours and then 50 miles per hour for 4 hours. How far did you travel? So I want you to compute this algebraically and then think about how you might draw the graph to represent this. So we did this with a single rate times time for this one. Now we have 2 different rates with times for this one. So how do we add in a second leg to our trip? Okay, so I want you to take 2 minutes, see if you can compute this algebraically, and see if you can come up with a graphical representation of what's happening in this scenario. And then we'll go through it together. Okay, take about 30 more seconds. All right. So again, we want to start with, we'll start with algebra. It doesn't actually matter if you start with the algebra or the graph. But here we want to start by doing our rate times our time. So for the first part of the trip, we're doing 20 miles an hour for 3 hours. So 20 miles per hour times 3 hours means on this part of the trip, we went 60 miles, right? Because again, the hours units cancel. The second part of the trip, we went 50 miles per hour for 4 hours. So again, the hours units are going to cancel, and that gives us 200 miles. And so our total distance here is going to be the addition of the two legs, right? Because we did this and we did this. So that's 260 miles. Okay, so that's how we would figure that out algebraically. If we want to try graphing this, okay, we have our rate, and we have our time. And again, both of our rates here are constant rates. Like when we're going 20 miles per hour, that's a constant number the whole time. Same thing for 50. So let's say 20 is here. So 20 miles per hour, and we do that for 3 hours. So time equals 0, 1, 2, 3. So we have this constant rate for 3 hours. So if we want to talk about this in terms of area, right? The area underneath is a rectangle. It's a 20 by 3 rectangle, which is where we get our 60 miles for the first part of our trip. And then we go 50 miles an hour for 4 hours. So when we do this part, we make the baseline assumption that we're starting at hour 3 and going the next 4 hours, right? So 4, 5, 6, 7. But our rate has changed. So now our rate is 50, which would be somewhere up here. So from time hour 3 to time hour 7, we are going 50 miles an hour. And so again, we get this rectangle. So we can compute the area under the curve here, where we're going to do 50 times 4, which gives us this 200. Okay, so what we would do is we would add up all of our areas, and we would get a total of 260 miles. So again, we have 2 different ways to represent the same scenario. Okay. The next problem is similar, only now we're not talking about driving, right? Just to sort of give you a sense that not all of these have to be about distance. We're going to see if we can translate this over to a population problem. So suppose a population is growing at a rate of 2,000 people per year for 3 years, and then 3,000 people per year for 4 years. What is the total change in population over these 7 years? So again, I want you to take 2 minutes, think about what is your rate, what is your time, how do we do this algebraically, how do we draw a graph to represent this? So take about 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. All right. So hopefully you're able to see that we can use the same processes and our rates just happen to be about something else. So here we have two different rates that are happening for different amounts of time. So the first is that the population is growing at a rate of 2,000 people per year. So I'm just notating the units here. And that happens for 3 years. So that means that over that 3-year period, so notice that the years units cancel, my population changed by 6,000 people. Now, after that, my population is changing by 3,000 people per year. And that happens for 4 years. So again, the years units cancel and I get 12,000 people. So again, I need to look at both of these changes and add them up. And I get a change of 18,000 people over the total 7-year period. Now, a really, really important distinction is that my population is not 18,000. My population changed by 18,000. I don't know what my population is because I don't know how much I started with. All I know is that it has gone up by 18,000 people. So when we do this type of calculation, we are talking about how much the original function changes over that time. Okay. So if we were to graph this, again, we have our rate, we have our time, we're looking over 7 years. Okay, so for the first 3 years, we're changing by 2,000 people per year. So again, that gives us this nice rectangle. That area will be 2,000 times 3. That gives us the 6,000. And then from years 3 to 7, we're changing by 3,000 people per year. So we bump up here. And again, we can also use the area underneath this line. So we have 4 times 3,000. That gives me 12,000. We add those together. And that also gives us this change of 18,000. Okay, so again, we have the algebra and we have the graph. Now, why do we need this graph if we can just use the algebra, right? You might be wondering. Well, it turns out that this only works algebraically if your rate is constant. If your rate is not constant, you cannot use the same algebra to come to these same conclusions. So let's look at an example of this. Okay. So suppose the rate at which a skateboard is moving over a 60-second interval can be written as f of t equals 3t, with f of t in feet per second and time t in seconds. Okay, so let's talk about this rate for a minute before we get too far. So what this means, since it's not constant, is that it's speeding up. So at time equals 0, the skateboard is moving 0 feet per second, because if you plug in a 0, you get 0. After 1 second, if you plug in time equals 1, the skateboard is moving 3 feet per second. At time equals 2, it's moving 6 feet per second. At time equals 3, it's moving 9 feet per second. So at every different instance of time, it has a different rate. It's not a constant rate. So we can't approach this the same way, right? We can't just multiply our rate, 3t, times our time, which will be 10 seconds once we get to the question. If we were to multiply 3t times 10, we would just get 30t, and there would still be a variable in our answer, which isn't super helpful. So we have to rely on a graph to figure out the area under the line. Okay, so the question here is, what is the total distance traveled by the skateboard over the first 10 seconds? Okay, so our time here is 10. Our function, instead of being constant, will be a line. And we have to figure out the best way to determine the area underneath that function. Okay, so I'm going to give you 2 minutes to try this out. I want you to graph the rate. Think about what a function that is 3t would look like. Put a 10 on the time axis and see if you can figure out what the area underneath that line is going to be. Okay, there's a couple small things you have to figure out, but I think you'll get it. So take about 2 minutes, try it out, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So, as I mentioned, we can't use our regular algebra here. So we have to consider what the graph looks like. Okay, so my function here is 3t. If I were to graph the function 3t, it would be a line that goes to the origin. It would look like this. I'm interested in what is happening during the first 10 seconds. So time is in seconds, and my rate is in feet per second. Okay. So if I'm looking at the area here, what I notice is that I don't have a rectangle, but instead I have a triangle. A triangle is a geometric shape that I also know how to find the area. So as a reminder, the area of a triangle is 1/2 base times height. Okay. So what I have to do is I have to figure out if I know those values here. So 1/2 is just standard part of the formula. My base goes from 0 to 10, and that represents 10 seconds. And then there's this height, right? So in order to determine this height, I need to take my independent value and plug it into the function to get the corresponding y value. So I would plug this 10 into 3t, and that would tell me the rate, which is 30 feet per second, right? 3 times 10 is 30. So again, I notice that my seconds units will cancel, and I have 1/2 times 10 times 30 gives me 150 feet. So I was able to determine the change in position, 150 feet, by looking at the area under the curve, right? Curve being a line here. So we're able to start to use this idea that area will tell us total change, okay? Now, if your rate is constant or your rate is linear, we're going to be using just the graphs with the geometry to determine that area under the curve. If, however, your function is actually curved, right? So something like a parabola, like, t squared, then we run into a little bit of trouble, right? Because if you have something like this and you want to get this area here, we don't have a good geometric way of doing that, right? We're not going to get into arc lengths and things like that. So what we do in math when we don't have an exact formula is we use what we do know how to do to try to retrofit what we don't know how to do, right? So what we do know how to do is find the areas of rectangles and triangles. What we don't know how to do yet is to find areas under things that are actually curved. So what we're going to do is think about how we can use rectangles and triangles to start to think about curved functions, okay? So consider this situation, okay? Imagine that you are in a bike race and whoever goes the farthest over 10 seconds wins $1 million, okay? And so we're going to measure your velocity in feet per second on a flat road that you're biking down, and we're able to measure your velocity every 2 seconds. So this is what the data looks like. So at time equals 0, you're not moving yet. The bell goes off and you start riding. After 2 seconds, you're going 5 feet per second. After 4 seconds, you're going 7 feet per second. After 10 seconds, you're going 22 feet per second, right? And we want to use this to figure out how far you actually traveled, right? And we've talked about this a little bit at the beginning. Distance equals rate times time. Now, how do we use this data to actually determine this? Well, we need to be careful. We can't just multiply the independent value times the dependent value, right? So if we were to multiply 10 times 22, that would mean we were going 22 feet per second for 10 seconds. And that's not what's happening here. We were going 22 feet per second at time equals 10, not for 10 seconds. So that's like an important distinction here. So as I mentioned, we want to retrofit what we do know how to do into what we don't know how to do. And what we do know how to do is deal with rates that are constant. If we have a constant rate, then we can do rate times time. So how do we make that work? Well, the first thing we want to do here is we want to break these things up into smaller intervals. Just like we had the 2 legs of the driving trip, we're going to have different legs of this biking. And so what I notice is that I'm measuring every 2 seconds. So what I'm going to do is I'm going to break this down into 2-second intervals, okay? And so when I do that, I get delta t equals 2. So my delta t is how big my interval is, okay? So from time equals 0 to time equals 2, that's going to be my first interval. Time equals 2 to time equals 4, do my second interval. Time equals 4 to time equals 6, my third interval. Time equals 6 to time equals 8. And then finally, time equals 8 to time equals 10, okay? So I'm breaking it up into these intervals because that's how this is presented in the table, right? Every 2 seconds. So I'm going to look at each of these intervals. And what I'm going to do is I'm going to assume that my rate is constant for those 2 seconds so I can use the formula rate times time. But since I'm doing this mathematically, I need to do this in a way that is consistent between intervals, okay? So bear with me for a moment. From time equals 0 to time equals 2, I have a velocity of 0 and I have a velocity of 5, okay? I'm going to pick the rate on the left because then I can pick the rate on the left for each interval and that will make something that is consistent. So from time equals 0 to time equals 2, rate times time, if I pick the rate on the left, is 0 feet per second times 2 seconds, okay, which gives me 0. From time 2 to time 4, I pick the rate on the left. So between 5 and 7, I pick the 5. So rate times time is 5 times 2, which is 10. Time 4 to time 6, I'm going to pick the rate on the left, which is 7 times 2, which is 14. Time 6 to time 8, I pick the rate on the left, which is 10. 10 times 2 is 20. And then finally, from time 8 to time 10, I pick the rate on the left, which is 15 times 2, which is 30. I need to add up all of these rates, right, to represent each leg to figure out my total distance traveled. So when I add these all up, I get 74 feet that I've traveled. Now, if you are the bicyclist and you are racing for $1 million, you would be very unhappy with what I just did. And the reason you would probably be the most unhappy is that I didn't even use your fastest time, right? I didn't use that 22. Now, what I just did was consistent, right? I picked the left-hand rate for each one, but that doesn't make it the most, what do I want to say, the most perfect approximation. What I just did is called a left-hand estimation. Okay, and we often abbreviate that LHE, left-hand estimation. So my left-hand estimation always picked the rate on the left. However, I could also be consistent by picking the rate on the right, right? So there's nothing stopping me from doing that. So I'm going to go ahead and do that, but I want to point out that for a left-hand estimation, I did not use the rightmost rate. Now, if I do a right-hand estimation, then as I go down each 2-second interval, I'm going to pick the rate on the right. So for the first 2-second interval, I pick the 5 as my rate. So 5 times 2, which is 10. From time 2 to time 4, I pick the one on the right, which is 7. 7 times 2 is 14. Then I pick the one on the right. 10 times 2 is 20. From time 6 to time 8, I pick the one on the right. So 15 times 2, which is 30. And then finally, from time 8 to time 10, I pick the rate on the right, which is 22. So 22 times 2 is 44. So now, when I add up all these numbers, notice that I didn't use the leftmost rate. I get 118 feet. Okay. It turns out that when we do this type of work, that the actual distance traveled is going to be bounded by these values. So that means that the actual distance traveled has to be between 74 feet and 118 feet. Okay, so somewhere in there. So what we often do is we use what's called a best estimate, which is to average the left and the right hand estimate. So we would do 118 plus 74 divided by 2 would give me 96 feet, because that takes into account, both the left and the right in using an approximation for how far you've traveled. Okay, so when we do this, what's happening when we sort of approximate a constant rate for each time interval is we are using these rectangles that we sort of forced in order to do this. So let me grab a piece of paper because we're going to draw a picture here. So what does this look like? Okay. So when we draw this picture, what is actually happening looks like this. So we have our rate, we have our time. Our time is in 2-second intervals here. So we have 2, 4, 6, 8, 10. Okay. So we're going to start by drawing our left-hand estimate, and then we will draw our right-hand estimate, and we'll see what the difference is here. So for our left-hand estimate, we are assuming this 2-second time interval, which we're calling delta t, that the rate is 0, which means we are right on this axis. And that means our rectangle doesn't have any area here. From time equals 2 to time equals 4, we're assuming that the rate is 5. So that's a constant rate. So that generates this rectangle, which we know has an area of 10. So I'm going to mark off by 10s here to help us sort of see what's going on. Okay, so from time 4 to time 6, we're picking the rate on the left, which is 7. So again, we're assuming a constant rate during that time interval, and that constant rate allows us to generate an area that is given by a rectangle. From time 6 to time 8, we pick the one on the left, which is 10. Okay, so again, we generate this rectangle, and then from 8 to 10, we have 15. Right? So these are our approximations. By picking a constant rate for that time interval, it generates these rectangles, which are areas that we know how to find. Now, this was a left-hand estimation. What if we did the same thing with our right-hand estimation? Okay, so for our right-hand estimation, we said, okay, well, for the first 2 seconds, we're going to assume the rate on the right, which is 5. From time equals 2 to time equals 4, we assume the rate on the right, which is 7. From time 4 to time 6, we assume the rate on the right, which is 10. From time 6 to time 8, we assume the rate on the right, which is 15. And then from time 8 to time 10, we assume the rate on the right, which is 22. It's going to be way up here. Okay, so we can see that the approximation from the right-hand estimate was bigger. Okay, the reality is that the actual function probably looks something like this, and we'll talk about why in a second. Okay. So with the left-hand approximation, each rectangle is touching the function in the left-hand corner, right? So for a time interval 4 to 6, it's the left-hand corner that touches. Whereas for a right-hand estimation, it's the right-hand corner that touches our function, right? So we get something that kind of has this idea. And what we notice is that the right-hand estimation is an overestimate. Okay, it's an overestimate because the area, we have more of it than is actually under the curve. Whereas the left-hand estimate in this picture is an underestimate because it doesn't capture all of the area. Okay, now you need to be really careful. The right-hand estimate is not always the overestimate. It depends on your function. So in order to determine which one is over and which one is under, you would need to calculate both, and the bigger number is an overestimate and the smaller number is an underestimate. Okay, but this is what we are doing visually. By fixing a rate for a small period of time, we are creating this constant line. Okay, now a couple of things that we need to be really careful about. So our delta t is 2. Your delta t is going to be the time interval you're using to approximate, right? And we got that from the table. So we were counting by 2s. That ends up being the width of all of your rectangles. N, we're going to introduce, is going to be the number of rectangles that you are using to approximate. So here's 1, 2, 3, 4, 5. So for each approximation, whether left or right, you are using 5 rectangles. That means that there's 5 time intervals that we are looking at, and that's based on the problem that you're doing. That will change from problem to problem. The other thing we need, A, is the leftmost endpoint. So here, that is 0. And then B is the rightmost endpoint. Which here is 10. And this will also change from problem to problem. It depends on what you are looking at. Okay, so let's look at a summary for a moment of just the different terminology we've just talked about for our approximations. So give me a second here. Okay. So what are the types of estimates we have here? We have a left-hand estimate. When we have a left-hand estimate, we assume that the rate on the left is constant. So this means that we have a table or a graph, and we are picking the value of our function on the left to make our constant value. We have a right-hand estimate, which is where we assume the rate on the right is constant. We have an overestimate. So here we compare the left and the right estimates and we choose the larger one. And we have an underestimate. That's where we compare the left and the right and we choose the smaller one. Then in terms of our variables that we're using to talk about these things, we have delta t. So these are our intervals for approximation. So what are we counting by? N is the number of rectangles we're using to estimate. And A and B are the start and end points as defined by independent values. Now, it turns out that there's a relationship between A, B, N, and delta T, okay? And that can be helpful to us in different scenarios. So if you were to look at B minus A, so the length of the interval, and divide by N, the number of rectangles that you want to use, that would give you your delta T. Similarly, if you took B minus A, the length of your interval, and divided by delta T, that would give you your N, the number of rectangles you are approximating with, okay? So taking all of this into account, what we want to do next is we want to think about if we change delta T, does that impact our approximation? Does it make it better? Does it make it worse? Does it make it stay the same? And what I want to point out is that if we were to change delta T, that would change our N. Or if we were to change N, that would change our delta T. Okay, so what we're going to do is we're going to take the same experiment that we just did. Okay, so suppose we're still on the bike, and it turns out that someone else was measuring your bike run. Okay, for whatever reason, there were many people measuring for consistency. And now we happen to know your speed at 1, 3, 5, 7, and 9, right? So we already knew your speed at 2, 4, 6, 8, and 10. Those are the same values we looked at before. But now we have additional information about 1, 3, 5, 7, and 9. So what does that mean? That means that now our delta T equals 1. We can measure every 1 second. We still need to now figure out our N. What's our new N? We'll talk about that in a few minutes. Our A is still 0, and our B is still 10. So we're still looking over this 10-second interval. So what I want you to do is, using our new delta T, I want you to come up with a left-hand approximation, a right-hand approximation, and use that to find the best estimate. Now, once you've done that, I want you to compare that to what we found in the example where we looked at this every 2 seconds. So the last example, and see if you can figure out, does changing delta T to 1 make this a better estimate or a worse estimate, or is it the same, right? So if we get the same exact interval that we had before, then delta T didn't change anything. Okay, so I'm going to give you about 3 minutes because there's a lot of little numbers to multiply here. Go through, find the left, the right, the best. If you can figure out N based on what we know, great. And then we will go through it together. Okay, take about 30 more seconds. All right. So as we do the left-hand estimate, we remember that we're not going to use the rightmost rate. So each number is going to be multiplied by 1, right? Because these are 1 second intervals. So 1 times 0 plus 1 times 3 plus 1 times 5. But we know that 1 times anything is just itself. So we have 0 plus 3 plus 5 plus 6 plus 7 plus 8 plus 10 plus 12 plus 15 plus 18. And remember, each of those was multiplied by 1, but anything times 1 is going to be itself. So when we multiply those out and then we add them all together, we are going to get 84. So our left-hand approximation is 84 feet, which we already recognize is different than the left-hand approximation we had before when our delta t was 2. Now, when we do our right-hand approximation, we are going to multiply everything by 1, but we are not going to use the leftmost rate of 0. So we have 1 times 3 plus 1 times 5 plus 1 times 6 plus 1 times 7, so on and so forth. And we go all the way out to 22. When we add those up, we get 106, which again is different than what we had before. So now our interval, where our total distance traveled needs to be, which I'm just going to call D, has to be between 84 and 106, right? Our distance. Now before, when we did this a few minutes ago, we found that that distance, where's my piece of paper? Hold on, I'm going to reference back. Where are you? Oh, I seem to have misplaced our first calculation. Hold on 1 second, everybody. Here we go. So before, our distance was between 74 and 118. Now it's between 84 and 106. And so this 84 to 106 is a better approximation because the interval is smaller, okay? So this is only 22 units long, whereas this one is 26 plus 18, 44. So since this interval is smaller, it's more accurate. So what does that tell us? The difference here was delta t. That leads us to believe that if delta t is smaller, which means you are measuring more often, that your approximation gets better. Okay, so keep that in mind because that's going to be important later as we go through chapter 5. Now, we also need to look at what the best estimate is here. So for the best estimate, remember we're averaging. So we have 84 plus 106 divided by 2. That's going to give us 95. So that's different than what we had before. In the last approximation, our best estimate was 96. Now it's 95. It's a small change, but it's an important one because if we're saying that this is a better estimate because the interval is smaller, that means that 95 is a better estimate than 96. Okay. Now, what about n? What's our n going to be here? Well, we can count. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 intervals that we're using. We could also have used our formula that we have b minus a divided by delta t would have also given us 10. So we did 10 little approximations to get these values. Okay, so what are some key takeaways? One, we need to make our intervals constant in order to approximate. Two, the smaller our delta t, the more we have our approximations, the better the overall approximation. Now, we've done this on a table, but how might we do this in another scenario? So the next question is going to sort of look at how we might approach this if we had a graph. Okay, so consider the graph below, which is the velocity of some object over 31 minutes. Okay, we want to estimate the total distance traveled using a left-hand sum with n equals 2, and we want to approximate a right-hand sum with n equals 2. So what does that mean? N equals 2 is the number of rectangles we are using to approximate. So we are trying to fit in 2 rectangles to approximate using a left-hand approximation, and 2 to fit in to do a right-hand approximation. Now, I want to remind you from our picture before that when we're fitting in rectangles and we do a left-hand approximation, that it's the left-hand corner of the rectangle that touches our function. So what do we need to do here? We need to find our delta t first. So hopefully, we can use this relationship, b minus a over n equals delta t. Once we have our delta t, we can fit in our rectangles, and then we find the areas of those rectangles to do our approximations. Okay, so I'm going to have you try this. I'm going to give you about 2 minutes to see if you can do a left and a right-hand approximation. Once you've done those, look at the values and determine which one is the overestimate and which one is the underestimate based on which one is bigger and which one is smaller. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. So first we start by determining our delta t. So we can use our two endpoints, which are 31 and 0, b minus a, and divide by the number of rectangles, and that will tell us what we have to count by to fit those in. So that gives us delta t equals 15.5. So the first thing I want to do is I want to label this on my axis so I know where 15.5 is, right? So 15 is right about here, so 15.5 is fairly close to where you get 15. I just want to make sure I label it as what it is so I can remember exactly, what value I was using. So let's start with a left-hand approximation to see what we got going on here. So my two intervals are 0 to 15.5 and 15.5 to 31. Okay, so I'm just going to try to highlight these intervals a little bit that we are using to approximate. Okay, so when I do a left-hand approximation, I think about the interval, so 0 to 15.5, and I use the left-hand value to become constant for that interval. Okay, so I go to 0, I go up to the functional value, and that becomes constant for this particular interval. Similarly, for the interval 15.5 to 31, I want to use the left-hand value. So I go up until I hit the function, then that becomes constant until 31. Okay, so again, I pick those values so that the left-hand corner of each one is going to be touching, right, my function. So I didn't do a very good job of drawing to scale, but these do have equal widths of 15.5. So the first rectangle here, to find the area, I'm going to do the width, 15.5, that's the time, how long, times the rate, which is the height. So the height here was 20. So 15.5 times 20 is going to give me 310 for that first rectangle. For the second one, I again have a 15.5 width, which represents my time. And now I need to multiply that by the height. So I have to approximate how high this is. And you may have approximated slightly different, but it should be in the same general area. I approximated that height as 17. So my rate there is 17. So 17 times 15.5 gives me 263.5. So then I have to add those two areas together, and I get 573.5 for my left-hand estimation. Okay. I'm going to do the same thing for my right-hand approximation, only now, when I look at each interval, the height will be determined by the rightmost point. So for my first interval, 0 to 15.5, I'm going to use the 15.5 to get the height. Okay. So that gives me this rectangle here. And so for that one, my width is 15.5. That height, that's the same height I approximated before of 17. That gives me 263.5. And then for my second rectangle, I have 15.5 and 31. I want to use the right-hand point, so the value at 31. But what I notice is that the value at 31 is 0. Okay, so I have 15.5 is the width times 0 is the height, which gives me an area of 0. So my right-hand estimation is 263.5. Now, if I compare my two estimations, 573.5 is bigger of the two. So my left-hand approximation is an overestimate, and 263, which is the smaller, is an underestimate. Okay, and again, you have to look at those two values to determine which is the over, which is the under. So that's how we would approach the type of problem we have here. If you have a picture, you would put in those rectangles based on n. So if we had n equals 4, we would have split this up into 4 intervals and done 4 rectangles. Here it only asks for 2. Okay. Another way that we might see this is with a formula. Okay. So here we have, if t is in hours of a 20-hour period, the rate at which a bacteria population is growing is given by f of t equals 3 plus 0.1 t squared. Find an over and under estimate of the total change in bacteria over this period if delta t equals 4. Well, in order to find an over and under estimate, we are going to need to find a left and right hand estimate. How do we do this? Well, just like our earlier examples, we need a table to do our estimations. We don't have a table, so we have to use the information here to generate a table. How do we generate the table? Well, we need time and we need the rates. Okay, we know that the starting point is 0 and the ending point is 20 because we have 20-hour period. So we know our A and our B. That's our A and our B. We are also told that delta t equals 4, which means that to get from 0 to 20, I am going to be counting by 4s. So I have 4, 8, 12, 16, 20. So delta t equals 4 means I'm counting by 4s. What I need to do is plug each of these t values into the function that gives me the rate. So for example, if I plugged in 0, 0 squared times 0.1 is 0 plus 3 gives me a rate of 3. Then I'd plug in 4, 8, 12, 16, and 20. Once I have those rates, I can then do a left and a right hand estimation. The bigger number is going to be my over approximation. The smaller number is going to be my underestimate. Okay, so I want you to take 2-3 minutes, fill out the table, figure out your left and right hand estimation, and use that to determine the over and under estimate for the total change in the bacteria population. Okay, so take about 3 minutes and then we will go through this together. Take about 30 more seconds. All right. So again, we generate our table by plugging each of our independent values into the function, and we get the following rates. To do a left-hand estimation, we're going to look at time intervals of 4 hours, since delta t equals 4. So for rate times time, for the first 4-hour period, we're going to pick the rate on the left. So we have 3 times 4, plus now for the next 4-hour period, we pick the rate on the left. 4.6 times 4 plus 9.4 times 4 plus 17.4 times 4 plus our last interval, we have 28.6 times 4. And again, we don't use the rightmost rate here. So when we plug all those values in and we add them up, we get 252. Okay, so the total change according to the left-hand estimate is 252 bacteria. Okay, since it's positive, 252 bacteria have been added. When we do a right-hand estimation, we're picking the rate on the right for each 4-hour period. So we have 4.6 times 4 plus 9.4 times 4 plus 17.4 times 4 plus 28.6 times 4 plus 43 times 4. So when we add up all of those, we are going to get 412. And again, when we do a right-hand estimation, we don't use the leftmost rate. So the question was asking about an over and under estimate. So we have to look at these two numbers and figure out which one's bigger, which one's smaller. And our bigger number is the 412. So our right-hand approximation is our over estimate, and our left-hand approximation of 252 is our underestimate. The other piece of information that's probably going to be important for us is what is our n. So again, n is the number of intervals you're using. So we can count. There's 1, 2, 3, 4, 5. We could do it that way. Or we could have used our formula, which is b minus a divided by delta t. That would also give us 5. Okay, and again, I just want to emphasize that your left-hand estimation could be an over or underestimate depending on the function. So you really do need to do both out to figure out which one is bigger so that you can determine which one is the overestimate and which one is the underestimate. Okay, so sort of to recap, if we do have a function here that's going to generate our rate, we need to use that to set up our own table for which we can then do the left and the right hand estimation. Okay, and we set up our table by figuring out the endpoints and our delta t, which will allow us to generate the correct independent values, and those get plugged in to get our dependent or rate values. Okay, so we're going to stop here because we won't have enough time to do the next piece. The part that we're skipping for now is not on your quiz, so you don't need to worry about that. The stuff that will be on your mini quiz will be the types of things we covered up to this. Okay, so have a good rest of your day. Don't forget about the review later today. And yeah, the link is in Moodle for that.